Good afternoon, everybody. I'm here today to present the paper entitled Compiler-Instrumented Dynamic Secret-Redaction of Legacy Process for Attacker Deception. I'm Frederico Araujo, and this is a collaboration with my advisor, Dr. Kevin Hamlen at the University of Texas at Dallas. The goal of our research is to remove or replace secrets in address spaces of running programs, yielding processes that continue running after redaction, but with no secrets in it. So if you think about it, having such capability can be beneficial for a number of applications. For example, if in the event of a program crash, we want to safely release process dumps to developer for debugging purposes, one could think of first redact the address space of that program before releasing that dump process, so that we don't disclose your secrets that could be stored in memory before the crash. Another example could be to design a strategy to mitigate the intrusion by which we redact the address spaces of process in response to attackers so that the enemy or the adversary cannot glean secrets that are stored in the process memory. And even another example would be to deceive or disinform attackers by replacing secrets at runtime with honey data. And of particular interest to us is to use this dynamic secret redaction capability to implement effective and efficient honey patching. So typically, the way we defend against attacks or probes against no vulnerabilities is to patch the target server against this vulnerability to protect against future attacks. And this is good, but it's still a missed opportunity for defenders. So honey patching proposes to, instead of just blocking or rejecting the connections, it proposes to clone the attacker process over an unpatched decoy that feeds the attacker with fake secrets that confuses the attacker into believing that his attack is successful when he's not. And there is a well-known challenge for honey patching, which is how to create this process clone in a safe way that we can allow the attacker to abuse it in the decoy. So to that end, we want to look at the process address space and find all secrets from the other users, for instance here, user 1 and user 2, and replace them or redact them with fake data without touching the secrets of the attacker. So a well-known technique to track the data flow of secrets as a program executes is dynamic taint-tracking, which basically instruments programs with operations that track the explicit data flows of secrets at runtime. And many applications use dynamic taint-tracking, for instance, to detect vulnerability in programs or prevent leakage of information, sensitive information, or even to analyze the behavior of malware. So to understand how this works, let's consider this example extracted from the Apache web server, in which we have this input stream that is partitioned into a username and a password delimited by this column characters. And then later on, we might want to safely release these secret passwords. So we have this safe free function here. And the question is, how do we test whether this character string S is a secret or not? So if I am a developer, I can use an API provided by LLVM's DataFlow Sanitizer and add this operational classification here that attaches a runtime label to the password field. So basically what it does, it instantiates a couple of bytes that get attached to that particular address in memory, and then it takes care of propagating those bytes as the password is used. And later on, I can check if that particular string that is given to that safe free function is a secret or not, and then choose which operation to take. So this seems nice, and it seems that to work in theory, But there are several challenges in applying this to large-scale software. So to understand, let's consider this example again. If I am a developer, if I wanted to track all flows of password fields, instance of password fields, I would probably want to grab the source code, if I'm for a naive way, and then find all assignments to this field, and then add the taint-tracking operation. Okay. The problem is that if I change this program just a little bit, the problem all of a sudden becomes much harder. So in here, I don't only have to track the assignments to P now, but also all aliases of P. So I have to deal with pointer aliases. And when we consider a program that has 2.2 million lines of code, this problem becomes intractable. So to address this problem, our research introduces and implements a mechanism through which developers can use type qualifiers to declaratively annotate fields in abstract data structures to denote those fields as secret. And then our modified compiler will take care of instantiate and introduce intent for those fields and track them at runtime. So there are several advantages of such an approach with respect to an operational approach, as I mentioned before. So first, there are fewer declarations than operations for user to annotate. Second, the compiler can infer and implement the operations from declarations. So it can do that automatically. And also, it gives the opportunity for the compiler to optimize the operational implementation using software that performs better. Our system provides three simple annotations. So we have a secret annotation that denotes a structure containing secrets. We have a secret string annotation that denotes pointer to non-terminated sequence of secret characters, and also a non-secret annotation that is used to exempt some pointers within a secret containing data structure of being tracked at runtime. So our framework called SynAC modifies and extends the LLVM compiler to take to instrument the source code with appropriate taint-tracking operations in annotated C code. So basically, first the developer has to annotate the data structures in the program, and then a preprocessor takes care of propagating those annotations through pointer aliasing and also memory allocation casts. And then the instrumentation pass implements our special semantics that results in a taint-tracking binary. So while developing this system, we found many, many challenges. And in particular, one specific challenge that we found was how to effectively and efficiently implement a semantics to track taint for this declarative approach. So to understand this, let's look at this problem again that I showed you earlier. So here, the developer has annotated that field password with secret string. And now the compiler has to correctly track the flow of secrets in this case. It has to correctly track the data flow of secrets through various pointer operations. So in particular, the arrow operator has to propagate taint through field access expressions. The address of operator also have to propagate the taint to its return value. And obviously, assignments should propagate taint, but we also need a special treatment for the referencing assignments. And finally, we need to have or take special care in how we handle freshly allocated memory. So the freshly allocated memory has to be tainted at the point it gets associated with the tainted pointer. So the core problem here that we have to solve to address all these issues is related to the definition of what the label of a pointer means. And to illustrate, let's look at this example where we have a pointer that is labeled with user1 and a value that is labeled user2. And then we have this dereferencing assignment from v2 star p. So the question is, what should be the resulting label of the thing that pointer p points to? And to that question, there are two standard answers. So the first one says that star p should just be labeled user2 because After all, it points to a data that belongs to user 2. However, in a secret redaction context, this is problematic because if user 2 is an attacker and he controls variable v, and he has access to the redacted process image, so the memory of the process, then he can grab for this value v and find the value of the pointer p that belongs to user 1. So this is potentially confidentiality violating. So to solve this problem, there is another interpretation of what a pointer means that says that the label of the thing that p points to should be a combination of the label of user 1 and user 2. And this semantics is called, we call it a pointer combined semantics because it combines the pointer, the label of the pointer with the label of the pointee. So it seems that this combined semantics solves many of the problems associated with the secret redaction problem. However, it goes a little too far because in certain cases, it leads to huge, huge problems in terms of over-tainting. So I'm going to first show you in which cases it works, and then I'm going to show you in which cases we need actually to do extra refinements to the semantics. So let's go back to our example where we had this data structure in which the developer annotated the field password with this secret string annotation. So now the compiler will take care of introducing the taint to this pointer password field. And then when we execute the program and the data flows into it, we have here when v2 assigns to the pointer password, what happens in here, because we are using this combined semantics, the pointer password imparts its label or its taint over the value v2 that is stored in it. So apparently this seems to work. However, this works in this case because here we have a specific case where the secret that we have, they are separated by the structure that houses them by one level of pointer indirection. However, if structures mix secret values with non-secret pointers, then all sorts of over-tainting label creep problems arises. To understand and to illustrate this, let's look at this example, very simple example where we have this linked list of secret integers in which each node in the linked list should belong or should be tainted with labels for a different user. So if we use a pointer combined semantics in here, what happens when we assign the value 1, 2, 3, 4 to the field secret integer? It gets tainted. It combines, right? Because the pointer is tainted with the label of the user, so it just gets that pointer, gets tainted with that pointer. But then, when we assign a new fresh allocated node and assign it to the next pointer in that linked list, it also gets tainted. And this is problematic because now we are propagating the label from the previous user to the next user, which during the referencing leads to over-tainting. It propagates the label of the user to the other integer, and in the worst case, all nodes in this linked list will get tainted with all labels. So, and this is a very common actually case, like a very recurrent structure that happens in large-scale legacy software, in which we have those region-based allocators or memory pools. Like systems like Apache and Nginx have lots of these constructions. So our solution that we've implemented to solve this problem is an enhanced semantics for taint propagation that is called pointer conditional combined semantics. And that basically says that the thing that P points to should be tainted conditioned upon the static type of the pointee. So basically, we say that the semantics dictates that if V has a pointer type, then we should use a non-combined semantics. However, if V has a non-pointer type, which means it's a value, then we should combine the label of the pointer with the label of the pointee. So to see how this solves our problem, let's look at our example again. So I assign 1, 2, 3, 4 to the secret integer, and it gets tainted because it's a value, it's a non-pointer value. And when I create a new node and try to assign to that list, then it works in the way we expected. You see, because node 2 is a pointer, then our semantics says that it should preserve the label of node 2 and not combine with the label of the pointer. So this contains the propagation of labels and support nicely our declarative semantics that should say that each node in this linked list should have the taint of a particular user or of a different user. So to see how we implemented this in LLVM, let's go very quickly through our implementation. So first, we have annotated data types that are annotated with this secret annotation that are defined as annotated attributes that get parsed into the abstract syntax tree and can be leveraged by our rewriting or preprocessing step. We also have non-secret and secret string attributes or annotations that are defined as quali-type qualifiers that are leveraged to propagate those attributes to the backend in the form of intermediate code. And those are leveraged during our instrumentation phase. During the rewriting step, we have two subphases. So in the first phase, in the analysis phase, we compute the list of all security-relevant data types. So we look at the source code, and we look for all structures and unions directly labeled secret. Then all aliases of such data types, and also all nested structures and unions containing security-relevant data types. And notice that this definition is recursive. And in the synthesis phase, we then wrap all these security-relevant data type allocations or memory allocations with a special wrapper, SIGNA-C or SIGNA-C alloc, that takes care of introduced taint to the memory reference returned by the allocation. So this is the special treatment that I mentioned earlier about memory allocations that we need. The instrumentation is implemented as an extension to the DataFlow sanitizer, and labels are implemented as integers that are stored in this memory space called the shadow memory. So basically, the shadow memory maps the application memory for each byte in the application memory, 2 bytes in the shadow. And it also supports this notion of how to represent the join of 2 labels. So when you have 2 labels, then it creates this dynamically growing binary structure, very efficient structure that is stored in this union table space. It also handles the case where you actually have to propagate taint across external libraries and APIs, in which libraries, where those libraries are not compiled with the framework, or which means they're not instrumented. So in this case, we can specify the propagation behavior from arguments to the return value with each function through this ABI list, or application binary interface list. And the instrumentation step is an optimization pass in LLVM that operates on intermediate representation code and that inserts optimized label propagation code as it processes each instruction. So here I show an example for the store instruction. And at runtime, the instrumented binary that is generated from this compilation process is accompanied by a very, very tiny runtime library that provides an initialization function and also the 2 supporting functions for tainting addresses and wrapping the dynamic memory allocators. So to evaluate our approach, we tested SIGNA-C in Apache, Nginx, and Lite TPD, and for various different characteristics. So in this experiment, we have instrumented Apache Web Server and have sent 100 requests to the server and have calculated the number of labels that got instantiated at every request, at each request. So basically, this is a tally on the number of labels. And basically, what we observe here is that without our approach with PCS, we notice this huge explosion in the number of labels. And essentially, after 68 requests, the web server process actually crashed running out of labels because of the huge combination that we observed in there internally. And without our approach, the server was able to run for many, many thousands of requests, actually above 10,000 of requests, without ever crashing. So actually, that's much more than actually the average time, lifetime of a worker process in Apache. In the second experiment, we've computed the number of bytes, actually, so the taint spread in memory. So this is also a tally on the number of bytes. And again, we observed that without our approach, the instrumented server over-tainted by a huge proportion. And to test this hypothesis, we've run our redactor that I'm going to talk a little bit about later, just after a few requests. And what we noticed is that after each redaction, the process would crash right away. Because of the over-tainting, the redactor would over-redact, causing the process to crash. And with our approach, that never happened. So we also tested the overhead of instrumentation, so in terms of performance, for 3 different application profiles, so a static HTML application, a CGI bash application, a PHP dynamic application, with several concurrence levels, so 1, 10 to 100 concurrent users. And in each test, we sent 500 requests to the server and measured the average overhead of instrumentation. And basically, we concluded that this is comparable to the overheads of other sanitizers in the LLVM family. So, as application study into further evaluation of our system, we chose honey patching. And as I mentioned, the honey patch, when detects the attack, it forks the clone over this unpatched decoy. So the problem is, how do we redact secrets from memory before we actually allow the attacker to run over there? So first, we instrumented the server with our PC2S, or our pointer combined semantics. And then we've implemented a redactor that scans the memory byte by byte and replaces the secrets from the other users with fake data. And we allow the process then to resume in the decoy safely. So to test the performance of the redactor, we've created this experiment where we had 500 malicious requests sent to the server and measured the response times. And in the bottom line, we see the response time without any redaction, just to measure the cloning overhead of cloning. And then we had the response times with our approach, the information flow-based approach. And in the top curve, you see the response time of a prior redactor that was implemented for honey patching that is based on pattern matching on the memory page files. And basically, we can see here that our approach reduces the overhead of secret redaction by a large amount. But you still may think that because this overhead is non-zero, an adversary could potentially exploit this time difference to uncover and unveil the honey patch. But the honey patch, so that's actually not true, because the honey patch implements an artificial delay in the reverse proxy that pushes the bottom curve up to the upper curve. So masquerading the response times of non-forking legitimate requests to the response times of malicious forking requests. So that becomes undistinguishable between legitimate and malicious requests, the ones that trigger the fork and the ones that don't trigger. So the problem here is that if the delay is if the gap here is too wide, then nobody would want to apply honey patching practices because this would delay the response time of legitimate users. However, with our approach, this delay is much smaller, which makes honey patching all of a sudden much more applicable. And we tested our dynamic secret redactor on real vulnerabilities, on real honey patched vulnerabilities, including the heartbleed and shell shock vulnerabilities. And to conclude my talk, we've proposed and implemented a methodology through which developers can declaratively annotate secrets in legacy source code that leverages this new pointer tainting methodology. And to support this declarative annotation scheme, we've implemented this new pointer conditional combined semantics that accurately track the flow of secrets as a program executes while containing the taint spread and label creep. And we've implemented as a use case for this dynamics, for this taint-tracking framework, a memory redactor for secure honey patching, and tested it on 3 production web servers. So with that, I conclude my talk, and I would like to take your questions.
If you have any questions, please come up to the microphone. while we wait for people to gather their thoughts, I was curious, did you get to look into why the static content had the highest overhead of the honey patching? I think it was like 2 as opposed to like 0.5 for a CGI application or the PHP application.
Yes.
That seems a little counterintuitive, right?
Yes, yes, because we only instrumented the web server application. So those applications like the CGI and the PHP application, they have also business logic, and they have their own process that they have the content generator that is generating the dynamic content to the web server. Those are not instrumented.
Okay.
So kind of the business logic amortize the overhead that you see in there. Yeah, that's the reason why.
So that makes sense. So that this process is only applied to the Apache web server and not the CGI application and the PHP.
That's why we observed that the overheads hugely increased.
Okay.
And with the static HTML application without caching, so caching was disabled, then you see this more reasonable overheads, which are comparable to the overheads for other sanitizers.
Interesting.
Yeah.
Cool.
Yeah.
More questions? So I guess the next kind of thing in my mind, right, is, okay, you're able to redact the secrets, but then how do you redact them, right? Because as you said, if you do the honey patching and you fork, but the attacker knows that they're now in a honey environment, well then, why'd you go through all this effort? So have you thought about ways to semantically redact, or? Yes,
we didn't implement any sophisticated way of redaction in this work because we were looking at performance and overhead. But yes, there should be ways, at least what we've been thinking, on how to infer from what the attacker is seeking and then use this information to differentiate the labels that we use to annotate the different secrets and replace them with appropriate honey data. So if you can exploit, because the framework already supports that, so we could probably differentiate different labels and then replace them with appropriate honey data. So yeah, that would be a way to do it.
Okay,
yeah.
Cool. More questions? Cool, well let's thank Fred.